Dr. Susanne Schwenzer will be joining us on stage shortly. Susanne grew up in Germany in a small village. I've forgotten how to say this now. Artsbach? Artsbach. Yes. Give you a hint, it's in Germany. It's near Bonn, and I think that's the last time you try and trick me up through this, but I could be wrong. She has always loved nature and people and wanted to become a journalist when she was younger. She credited her father with making her realise that some of the coolest jobs needed a degree or perhaps even a PhD. One day, at a university open day, she discovered mineralogy, not because it was what she wanted to do in the job, but the prospects that topic might bring. It taught her all about the planet and how it works. And she wanted to become a journalist anyway, so why worry about what the job path is? She studied mineralogy at the University of Mainz, yes, and worked as a freelance journalist. And with a degree and a master's in mineralogy, she was torn between continuing to study for a PhD or to go straight into journalism. Well, both her parents had a PhD, and so...
No pressure.
No pressure, no pressure at all, but, did add to the perhaps, get one yourself. Besides the love of journalism, she loves lab work, working out how a piece of equipment worked and how to run it and how to get the best results possible. And during her master's degree, she spent a lot of time with mass spectrometers. And that's when she saw an advertisement for a PhD that would use a mass spectromic technique. I told you there was one time you tripped me up. I didn't think there was going to be quite so many. That she did not yet know a noble gas mass spectrometry. I got it right. It's all good. That piqued her interest, and she applied to it. And just to learn, not only did she get the job, but the samples she would investigate were meteorites from Mars. Yes, the real planet Mars. And you can ask her all about that later. I'll leave that one with you. She worked with Max Planck Institute of Chemistry and completed her PhD and postdoctoral position working on Martian meteorites, and then went to Houston, Texas, working with the Lunar and Planetary Institute, looking at rock-water reactions. That's always hard. And yes, Mars did have water in the past. It didn't always look quite like the desert that we see today. And Susanne has investigated how the water reacted with the rock when both heated by impact craters. She came to the Open University in 2009, using her skills working on noble gases in earth rocks, in meteorites, and continuing her work on rock-water reactions. It's one I can never do, and I'll hand you over to the specialist who'll get it right every time in a minute. All of this brought her to the NASA Mars Science Laboratory Science Rover Curiosity team, teaming up with Professor John Bridges from Leicester, where they were selected as participating scientists in the mission in 2011, just a few days before Curiosity's launch. She now serves as a Geoscience and Science Operation Working Group team leader. Susanne is also part of the ExoMars rovers team. And if you want to hear about that and that rover, come back tomorrow, where we have Dr. Elliot Sefton-Nash, who is the deputy scientist on the ExoMars rover. You can sign up for that one on the way out. But back to where we are tonight. It is my pleasure to hand over to Susanne, who's going to tell us as much as she can fit into the next 45 minutes about the Curiosity mission, all 12 and more years of it. Susanne, over to you.
Thank you, Hannah. That was fabulous. It's always a bit embarrassing to hear about yourself. But before I start, I want to do something else. Events like tonight are absolutely impossible with the myriads and myriads of volunteers and of staff working it. So let me start with the OU staff. We have staff from Astrobiology OU, we have staff from the STEM faculty, we have staff from central places here at the OU. You saw the catering earlier. We have people who move barriers, who set up things, estates. We have so many people from the OU who are working here today, not to forget Sam, who is silently whizzing away behind that glass screen up there, giving him a wave right now, to make the sound travel. So let me first thank all the OU staff and volunteers. But we are not alone. And there is one person who actually could help you say Arzbach because he knows the town and played football there. And these are from the IF Festival. We have staff and loads of volunteers from the IF Festival here. Without you, that wouldn't be possible. If you see a blue or a pink shirt, these are volunteers from the IF Festival. Some are helping in this room, some are directing the car park, and so on and so forth. So please also give a hand to all the fabulous IF Festival volunteers. Thank you all so much. Without you, that wouldn't be possible. And without all of you in the audience, I would not have a reason to stand here. So let's get started. What you are looking at here is actually where Curiosity is right now. And you see some of these ridges, and you see the rover tracks in the middle, and you see the landscape. And what's in the haze back there, that's actually the crater rim. And it's about 90 kilometers away. So that's the picture you are currently looking at. And how we got there, that's the story of the next about 40 minutes. But before I say this, Hannah didn't quite mention Astrobiology OU. Astrobiology OU is a fairly young group here at the OU. It was founded in 2019, just before that thing called COVID happened. And we are a group of about 60 scientists. Most of us work in other roles at the OU as well, as I do. I teach as a professor, and others work in other roles as well. And what we do, we have come together to research astrobiology as a cross-faculty, cross-discipline theme. And so, of course, we look into the biology. Where on Earth can life thrive in the most extreme environments to inform other environments and the search for life outside Earth, because we haven't found any life outside Earth yet. But if you search for something, you need to know where to look. That old joke, oh, I looked under the street lamp because I had light to look for my key. It doesn't work that way. If you didn't lose it there, you won't find it there, no matter how much light there is. And so we try to find out where to actually look. And I am a geologist, mineralogist, Hannah, you need to turn this around. It's water-rock reactions, because that's much easier to say. It's the same thing. Water reactions doesn't roll off the tongue that easily. So that's what some of us do. And but we also look at the astrobiology ethics. When we do this research here on Earth and outside, we want to do it ethically. And we also look at the law and governance. And my colleague sits just there looking at me, who does that. And we research into planetary protection from the science aspect, but also from the governance aspect. And so we span 3 faculties and 7 schools, and if you want to know more, I'll be out at the Globe later, and I can tell you all about this, because now we are getting to Mars. This is the Curiosity rover. It landed on the 6th of August in 2012, and this picture is about, oh, time flies, 2 years old at Montmartre. That's a little feature in the background. How do we name things? Well, we pick names of lists and say, you are named this now, you are named this now, and that's all that there is to it. This is the Curiosity rover. It got a bit dirty in 12 years, didn't it? And what you see here, and I hope it's okay to wander over here now, point a few things out. So, first of all, we have a bogie of 6 wheels, and you see some holes in the wheels. That's what happens in 12 years. We have some inlets here for instruments inside. We have all the cameras up there, of course, and we have a turret, which is just in front of the rover, which has a lot of scientific instruments on it. So what we can do is taking pictures and investigating the chemistry of rocks and the chemistry of the atmosphere. And what I will do is give you a whistle-stop tour through a few things that we have done, and then I just open the floor and you can ask me anything you ever wanted to know. Here we go. This is Sol 84. Sol is a Martian day, and we don't call it just a day because an Earth day is 24 hours long, as we all know, and it could have a 25th. We sometimes could use that, but it doesn't. Well, Mars almost has. It's 24 hours and 39 minutes. So if you were on Mars, you get an extra 39 minutes in your day. But that's why we call it Sol and not simply day. And so on Sol 84, we were nice, clean, intact wheels. And on Sol 3303, we had some holes, dust all over, so a bit of wear and tear. But the rover is still fully functioning. And it was designed for a 2-year mission. Now, you do the math. We have 2025, right? On 6th of August, we are 13 years on Mars. So what did we do? we started at Bradbury Landing, which is just to the right of that yellow circle on this screen. And many of these slides are credit to Ashwin Vasavada, who is the project scientist, the leader of the rover, and he was nice enough to feed me with some nice graphics, including that one, which I will use to show you the mission progress. So our first stop was Yellowknife Bay on this yellow circle down there, and we did that because we saw that there are 3 terrains coming together, and we wanted to know which is the older one, which is the younger one, and if you are at a place where these come together, we went there because we always wanted to go all the way up where it says Geddes Vallis Channel. But so it's not the most direct way, and we also didn't take the most direct way. Well, all that is black there are sand dunes. You do not want to traverse over sand dunes because, you know, there are no tow trucks on Mars. If you get yourself stuck, you're stuck, and we didn't want that. So we needed to find that gap in the dunes to go around. So we went to Yellowknife Bay. We found clay minerals. We knew we had a lake at Gale as early as Sol 100 in the mission. And then we went on the rapid ascent route, which we called it. We went past Kimberley, Paramp Hills, Murray Buttes. And from there on, we slowed the mission down a little bit. And then we went across Vera Rubin Ridge, the Glen Torridon, that's the clay-bearing unit. That's where we really could investigate that lake. And then we started to climb the hill. And when we climbed the hill, we learned that Mars is getting drier and drier. Because down there at Yellowknife Bay and in Glen Torridon, we have lots of clay minerals. Minerals that are laid down by water, that are laid down in lake beds. But the more we climbed, the more often we saw sediments that were more like dunes in the Sahara Desert, made into rock. And so looking at all of this, we are climbing up the Geddes Vallis Channel, and I show you more close-up pictures in a moment of the rest of the traverse. And we could see that the water interval is getting smaller and smaller. So the time that there was water is shorter and shorter. And the desert, the Sahara dune intervals get bigger and bigger. So it was drier and drier on Mars. The last dated point that we knew there was water on Mars is 2.6 billion years ago. The rivers on Mars that you might have seen on that beautiful globe down there are about 3.5 billion years old. Now, remember where that Geddes Vallis Channel is, because we are looking at it a bit more closely. You see we came up that Geddes Vallis Channel, and that's now a map view from the top. And by the way, this is the WebGIS. If you type, where is Curiosity now, you can go to this place and you can browse every single stop we have ever done. It's an interactive map. You see the plus minus works just as Google Maps. So we went into the Geddes Vallis, and you see we take these wiggly lines, partially because we want to go to places to investigate them, but partially also just because of traversability. If you go hiking in steep terrain or something, you need to find a place where you can actually walk and not fall down. And that's what the rover does there as well. And it's a 1-ton vehicle, 2 meters high, so it's a bit of a thing to feed through these landscapes, off-road driving. And so we did that, we went down there, and where it's blue, that's approximately where the rover is now. So let's zoom in and look at this a bit more closely. What you see here is you have to the right this mottled, lumpy terrain, and to the left where the rover is now, you see all these straight lines. We call this the boxworks, and that's the picture you saw at the very beginning with all these lines. That's where we are now, and at the very end of the talk, I show you a picture that came down from Mars this morning at 4 a.m. So this is where the rover is exactly, well, I took this screenshot a couple days ago because we traveled here. This is a sand patch. We traveled up here, and the rover's sitting right there. As I talk, the rover's here. So with that, and I promised Sam to not run around too much, how big is the rover? This is a model, a scale model, and the person here is Roger Wiens. He is just my height, so now you know how big the rover is. Roger Wiens is the principal investigator, the person who led the building of the laser instrument, which is just above him in that white box. Now, what have we learned? This is the 6th of August picture, and I always get goosebumps. We landed on 6th of August. You see these dents, these disturbances. That's the retro rockets. we had a hovering platform that lowered the rover, yet you see where the retro rockets hovered, and they blew off all the dust and the fine material. And there are tracks that start. Something started there. And of course, we checked out everything. We checked out the rover instruments. But then we drove on, we turned, and we backed up, and we photographed our tracks. And that's when we knew we had a mission. Because if the wheels hadn't worked, we wouldn't have a rover mission. We only have a rover mission because we have wheels and we can turn. And then we kept driving, and we are now on Sol 39. So you see how young the rover still was. And we discovered this. And we stopped and said, oh, what is that? They are very coarse grained, because you see the 10 centimeter scale bar, and you see all these grains in this upturned part of the rock. And now let me zoom in. This is a big guy. It's 2 centimeters. The Martian atmosphere is only 6 millibar thick. It can't move big stuff. Also, it's rounded. Aeolian sediments or flash flood sediments, if you just have a bit of water and it rushes down, they don't make round things. You need sustained water to make things round. It could either be the shoreline where it goes back and forth and back and forth and back and forth, or it is a river that rolls them down. So, Sol 39, our very first discovery, we had sustained water on the surface of Mars at Gale, probably 3.5 billion years ago. Here we go. And what can you do with it? You can count these. You can go and say, okay, this is one, and it's round, and it's this big. And you can count all of them. On the right, this is Earth in the Atacama Desert. On the left, this is Mars. And you see the similarities. And geologists quite often draw on these similarities, because when you draw on similarities, the physics works the same on both planets. You can start to understand what happened there. So what you see down there is one line in red. And sorry, if you can't see the color, it actually doesn't matter, because what I need to say is there are 3 lines of the gravels, how they look on Mars, on 3 different places. And there is one line, how they typically look in the Atacama in these river delta deposits. And you see that there is no difference between these lines. So if you can't distinguish between the color, you can't distinguish the lines, they all look the same. And that's the point that I'm making here, because we understand Earth, because we can observe it and walk up and down, we can draw inferences to what happened there. And we know the size of the pebbles, 2 to 40 millimeter, and so we can actually say that we had a stream that was about ankle to hip deep, and it flowed at a velocity of 0.2 to 0.75 meters a second. That's not very fast, but it is a stream. It wouldn't be dangerous to wade through, but it is a stream. And we have a bit of an error bar there, because we don't know the slope it came down on. If we could figure out the slope, we could narrow down how deep it was and how fast it flowed. So that was our very first finding. The second one came about 150 sols later, on the 270th sol. And there is a date that I currently can't read, 27th of January 2013, and I can't read it because I have a curtain in front of me. We did a drill hole here, and these are mudstones. These are the very, very fine things. And these very, very fine things, they only deposit if the water has come to a stop, like if that river flew into a lake, and then everything could settle. So you always have coarse grained things at the bottom, and when the water gets slower and settles, then the fine stuff settles as well. And so from all of these things, sedimentologists can read these rocks and the history of these rocks like a book. Well, we did our very first drill sample here, and oh, the red planet just gets gray. What happened here? Well, actually, the gray is the natural color of these rocks when you drill them, when they are completely unaltered. The Martian surface is red because it gets oxidized. And it gets oxidized because what little water there is gets split into hydrogen, which leaves the planet, and the oxygen, which is free to oxidize the iron. And that's why Mars is oxidized. There is radiation that adds to this, so there are a lot more factors. And how deeply that penetrates into the rock is different for different rocks. And so we were really surprised to find here gray rock. And this is the rock we found the most organic molecules. And I need to say organic is not biologic. Biologic molecules are usually organic molecules, but you can make organic molecules, which simply means there is carbon in long chains, that's all that this word means, without any life attached to it. So that's the rock where we found the most organic molecules. And it could be because it is not oxidized, it is so gray. Now, let's go on and see what else we found. Sol 126, I'm jumping around a little bit here in the early mission. We found these sediments in gray on the left, and on the right you see, again, an Earth analog. We don't bring pocket knives to Earth, to Mars. You see these white veins in the Earth rock and the mud in between. And it looks exactly the same on Mars. And so they said, some veins. On Earth, we know they usually form when you get a crack and it gets water-filled and the minerals from the water get deposited in that crack. So what is that? Well, ChemChem to the rescue. The ChemChem instrument, that laser instrument you see on top here. And it's a picture, of course, in the lab there. We also don't bring clocks to Mars. So what we have here is we have that laser instrument up there, and that laser shoots at a distance of typically 2 to 3 meters. And why do we bring a laser? We also have an arm instrument that's chemistry, but for the arm instrument you need to be here to put it on the surface. But our rover is really slow. I mean, 4 centimeters a second. I need to hold on to the lectern that I can walk that slowly, right? So we really want something that can say, is that rock the same like that rock? And that's the laser, and it returns really valuable data. We also have all of our eyes here. You see the M100 and M34. These are 2 mass cameras with different focal lengths. They have an overlap. We can do stereo, but they can also focus on different things. And we have 2 sets of navigation cameras. They also do stereo, the upper and the lower, A and B. And they are actually the eyes of the rover. It's a grayscale because we don't have that much bandwidth. And we can do stereo imagery of our landscape every single day. They are working, and without the nav cams, without these eyes, you can't drive a rover, and that's why we have redundancy. Now back to our little rock and ChemChem. So ChemChem, first of all, investigated the vein on the top. And the vein on the top, and Sam, I'm sorry, I have to walk again. He needs to do the camera. What we have here is you have the magnesium, and you see that black line, which is really high here, but not so high here. It's only the one that goes to the half width. And that means that is our reference spectrum. And that reference spectrum means this would be the normal rock. If you compare that with the red spectrum, which is only this high here, almost not here, and goes all the way up here, something is very different. But it is not different enough to draw a conclusion, because it just is a bit different in the heights. So that little point up there could have actually met rock and white vein at the same time. So what we needed to do, find something where we only hit the white vein. And we have that. And it's a little bit easier to discern because we have actually black and blue here in the lower slide. You still see that black spectrum everywhere. And you see we all have almost no magnesium, almost no silica. There is no blue under the aluminium. And there's a lot more calcium. So what we have found here was a calcium sulfate vein. Just with one laser shot we could do. And then we see all these mineral veins. Suddenly you see them everywhere. And that's where the water-rock reactions and where my research comes in. So you have these rocks, they fracture and they have groundwater coming through, and that deposits all these minerals. They are calcium sulfates, the mineral gypsum, or anhydrite, depending a little bit on temperature and how much salt is in the water. But we have other signs of water too. This is old soaker. And if that reminds you of your garden puddle when it dries off in the summer, that's exactly what that is. It's mud cracks. And mud cracks, I have a picture of Earth, Utah down there, and the image credits are always at the bottom because I stole this from Wikipedia. It rained too much in my own garden to take them there, for a start. So what we have here is repeated drying and wetting of a clay-bearing surface. That's how they form. And England is a perfect place because it rains all the time, then it dries off a bit and it rains again. And so we see a lot of these mud cracks, and what that means on Mars is that we are just at that boundary where we have dry days and wet days. And so that is very, very exciting. And from there, we drove into the actual clay-bearing unit. You might remember that I said the Glen Torridon area, and that's the actual clay-bearing unit where you see that light-toned material, all the cracks. We have a lot of clays there. To get you oriented about this dark straight line, that's the green pediment that we tried to climb on and drive over, but we couldn't because it is so rough and we would have completely destroyed the wheels. You never destroy your rover. No science target is that good. So we went all the way back there around and came back up. And while we did this, we found something. We found how the mineralogy changes. I pointed out to you that we have instruments in the belly of the rover. And so these instruments in the belly of the rover, they give you mineralogy. What is actually there? And just tells me where it has, how it has formed. How have all these minerals formed? Are there any geologists in the room? No one raises their hand. Everyone sits on them. Okay, I think I've spotted at least one or two. So what we have here is in the lower four, you have a wedge that is green. And that green wedge, which is on the left side of these pie charts, is clay minerals. If you then look at the, that says TP and BK, and these are just names that we leave out for now, in the Param Hills, there is no green in these pie charts. Then at OD, it comes back a little bit, and MB, QL, and that's Marimba, Quela, and Sabina, they have clays again. And that tells us how they formed. That big blue wedge, that's crystalline silica, but that's only there when clay is either very little or not there at all. So something has changed here. And something has changed here that the rover measures. That's my work, the water-rock interactions. I always say it that way around. And what you are looking at here is a diagram where you have the water-rock ratio on the bottom, goes from 1 kilogram of water and 1 kilogram of rock, like just in baking, you know, 1 on 1, all the way to 100,000 or something. The curtain is in my way. And what you see is lots of wiggly lines. And what I want to draw your attention to is that these wiggly lines change if you have comparably little water at the 1-to-1 ratio. You have a much more varied composition with many more lines that also come higher up than on the right side, where you're completely dominated by that green line, which happens to be a clay mineral. And also on the top, that hematite and magnetite, that is two different minerals that would tell you what the redox is, like how much energy could a microbe find if it were living there. And it could find a bit more when it were living in a system that's formed on the left side, or forming at the time in the left side, than it would on the right side, coming back to astrobiology for a moment. And so using these diagrams, we also get a fluid, the who's done it. You see all these minerals, the who's done it, like in a good crime scene. I know we have at least one lawyer in the room. In a good crime scene, you never know who's done it. You need to figure this out, right? And we can do this with these models, and then we get the water, and we get the who's done it. And then we can take the water and in a computer evaporate it. And that's when you get the gypsum and the anhydrite, the white minerals. So we can actually follow all the steps that these rocks did 3.5 billion years ago in a computer and recreate them and learn how much energy would there have been for microbes. We can learn about the temperatures at which that happened and the water to rock ratios. Now, but we have more evidence. We have evidence, for example, in wave ripples. Here you have visual evidence of wave ripples. And what I'm doing here is I'm putting a picture again from Earth in here. And these wave ripples, they are actually very symmetrical, and they bifurcate like a tuning fork in some of these places. And what you see down there in this Earth example is that this is how this happens. And we can draw an analogy from where we know things on Earth to what has happened on Mars a while ago. And now I'm coming to a few pretty pictures. Pareto P2 Pass. We climbed over a very, very small sand dune at this point, and it's just a beautiful picture. And in these hills, you can see all the layers of rock that we can read like a history book. Now, very special treat. All of our drill holes You recognize the one in the upper left corner, and that's gray. You see some are darker gray, some are very red, they are very oxidized, and they are all just 2 centimeters, under an inch in diameter, and 6 centimeters deep. And so they are very little sampling drill holes, and they just appear here, and they all look different. This is 43, I think. We now have sample number 44, just drilled 3 weeks ago, called Altadena, after the town where JPL almost is. It's in Pasadena, which is just to say, Altadena is Upper Pasadena. It was in the press in January with all the wildfires, and a lot of my colleagues lost their houses. But so we named that drill hole after that little patch of land on Earth. So here's a model of what happened at Gale, and the model circulates as a GIF file. It will circulate a few times, but that's what also happened on Mars. We had a lake with all the tributaries coming, feeding the lake, which then dried out, and maybe it filled again and dried out, and the intervals of wet got shorter and the intervals of dry got longer. So, what do we do to interpret this? This also is a GIF. You see the colors. The clay-bearing unit, where I said we've learned all about the lake and the clays, and that's in the bright green. And then you have this turquoise color which comes up, the green pediment, where we couldn't travel. It's very hard rocks, and we couldn't travel over them. And then there is this red, the Geddes Valles Ridge, and that's what we wanted to reach, and we just could reach it at one point overall, simply because the traversability of the green pediment is so bad. And this picture ends in the middle of the Geddes Valles. We have now driven between these 2 yellow mounds to the left and up. And what have we found? Well, Mars also has an atmosphere. We have Martian dust storm season, and this is the Duluth drill hole on the left before the dust storm. And during a dust storm, you don't do anything with a rover. You hunker down as much as you can, and you wait it out. And so we drilled the Duluth drill hole. We saw the dust storm coming. And so we stood there. We closed all the shutters that we could. We pointed mast cam down so it wouldn't get the lens sandblasted. And we took that picture during the dust storm. They are the exact same exposure, and now you know how much dust was blowing around there. It would have gotten really, really dark. But there are also dust devils. Look at the inner part of that square that's drawn there on the left, and you see him coming. It's not a video, it's a sequence of images, and you see that dust devil coming through. That's a 6 to 10 millibar atmosphere. Blowing dust around. And because it's so thin, they look like little tornadoes, but they are really just dust devils. They would sandblast you, but they wouldn't blow you over. Now, let's investigate the atmosphere a little bit. This is a SAM instrument, and it has loads of things. All I want to say, it has atmospheric inlets. It can let the atmosphere in, and it can, when it lets the atmosphere in, ingest it and look for that elusive thing, methane. We all know methane because, you know, cows. But why do this is a Texas Longhorn, by the way, and that's Johnson Space Center in the background. It's not my image, it's a NASA image as well. They are actually quite shy. This is the Saturn V rocket facility that you can visit if you ever make it to Houston. So this is a cow, and why do they emit methane? Well, they emit methane because in their stomachs, where there is no oxygen, it's called an anoxic environment, there live bacteria that have a metabolism that doesn't produce CO2 or anything. It produces methane as a waste product. So what we learn from these cows is if you don't have oxygen and the Martian atmosphere only has 0.13% oxygen, Earth about 20 in the atmosphere, and plus the Martian atmosphere is much thinner, so it's even less. So any bacteria would not have oxygen to fulfill what they do on Earth. So we need anoxic bacteria. And we are looking for methane, therefore. These are all detections before Curiosity arrived. And are there any youngsters in the room who like to take a test after? Well, I'm sure they are smart youngsters, and they would just memorize these two numbers. The 3 is the lowest value, And what it says is ppbb, parts per billion per volume. So parts per, so much, so self-explanatory, billion, 1 billion particles per volume. So in a billion particles, in any given volume that has a billion particles, there are 3 methane molecules. Go find them. And up there, the highest value is 45. Not quite much better. But curiosity actually can. And so what we have done is we have measured over the different seasons of Mars all of these methane. And the black curve you see is actually the pressure curve of Mars. And so if the pressure is high, we measure a bit more. If the pressure is low, we measure a little less. And what we also have here is this outlier, which lies at 21 parts per billion per volume. There's actually another one, which is even higher. It shouldn't be there in that season, and there are some outliers. We haven't fully explained them yet. And what we think is just that there's methane stored in the crust and that suddenly comes out. And I see you all peek up. Does she now tell us there was life on Mars? Unfortunately, I'm not there. And if I were, Hannah would probably have had a Nobel Prize on my list. And so she didn't say that, so we haven't found life on Mars. Very, very easy. So what we have here is we have either the pathway that I was talking about all the time, microbes in water, and they make methane, and we could store that methane in clatrites, which is a special ices, porous ices, or in clays, or. So there are many variabilities. However, there is a second way, and we know that this would be there. If we have water, and if we have the rock olivine, if that reacts, then what would happen? We would get hydrogen. And you add the CO2, which is what the Martian atmosphere is made of, and you make methane from the hydrogen from the water-rock reaction and the CO2 in the atmosphere. We know there's olivine in the rocks. We know we have water to react them because we see the minerals that creates. And we know there's CO2. So what's the easiest explanation for the methane? That. So we haven't found life on Mars. And that methane then goes on to outgas, and it is hit by UV, but there's also cosmic dust coming in, which is organic molecules that have nothing to do with biology. They can degrade, make some more methane, but then all the radiation on Mars will break that down over a few steps and make carbon dioxide. And carbon dioxide is the main constituent of the atmosphere, so you will simply never find it again. Let's get back to more happy topics, because we still can't find a rover on Mars. And so we climbed the Geddes-Wallace Channel, which looked really, really beautiful. Here are some pretty pictures. That's the Geddes-Wallace Channel. And suddenly we found this. White things. Oh, is that the same stuff as the veins? Could well be, right? Couldn't it? But then we cracked one open with the wheels. And when we cracked one open with the wheels, we saw it's actually yellowish. And then we measured it. And it is not the calcium sulfate that all these veins are made of. It's pure sulfur. What? We haven't explained that yet. You see the date when we first found it in 24. We haven't explained it yet. It's so weird. And that's what makes my job so interesting, because if you can't explain it, it gets really interesting. On Earth, you would find it around volcanic vents. There is no volcanic vent here. But Mars is different. The atmosphere is different. And so we are still trying to figure this out. And there's so many of them. All these white stones are pure sulfur. Where do they suddenly come from? Why are they there? We don't know. Stay tuned. And so what we have learned, Mars had long-lived water once upon a time. And in that long-lived water, we had salts. This is a place I had the great fortune to stand here on Earth. This is the Makati Basin down in Botswana. And I took this picture of salt. That's table salt, sodium chloride, which is really, really soluble. You all know this when you use the salt shaker, right? And so this is the surface in the Makati Basin. And of course, then there's the wet season and the water comes back again. And we know that Mars, once upon a time, has looked just like this. And of course, we know that there are living things, especially microbes. And that's what my colleagues did when we were there. Looked at, and they live there. And so what we know, to just summarize a little bit what I have been saying, Mars had long-lived liquid water. It had all the chemical key ingredients and nutrients for life. It had sources of energy to sustain life, and it had a lack of extreme temperature and salinity and acidity at some point in the past. But that isn't the case anymore. So we had a warmer and wetter period, maybe warmer, surely wetter. And those of you who have mused over the globe already, you saw that smooth terrain on the top. Well, that smooth terrain on the top would have been filled with an ocean. Other low-lying areas, the one that is filled with clouds on the globe out there is down on the right there, filled with water as well. Gale would have been filled with water. Every big hole is filled with water, just in the Lake District, you know. Every hole is filled with water. And then Mars would, over time, have dried out to what we see today. And we say the Noachian period is the wet period. It's the oldest period, went to about 3.2 billion years ago. Then we have the transition into the Hesperian. And about 3 billion years ago, the last water on Mars got lost. Well, there's still some in the polar caps, but liquid water wasn't stable on Mars anymore. And that's because the atmosphere is so thin. It just would boil, and it would be gone. It would be gas. And today, we have a dry and cold Mars. And I want to end this talk with two pretty pictures. One is this. It came down at 4 a.m. this morning. It was measured on the 18th of July. It's a Mastcam image of our turret in the Martian landscape. And on the 18th of July, we had Sol 4603. So, and I've talked about clouds. I've just mentioned them again. Here are clouds over Mercure. And with that picture, I just say thank you for coming, and I'm here for any questions. How did I do? Did I overrun too long?
No. As always, Susanna, you were perfectly timed. But yes, no big surprise. Imagine if I'd missed that off your list of things. That would have been bad, wouldn't it? But someday soon, maybe I'll be able to add that to your list of wonderful achievements. So we have 15 or so minutes for questions from anybody in the crowd. There's a hand gone straight up. We have two people with microphones who will come to you. So if you can just be patient, then we can hear your questions. So we'll start with the gentleman at the back.
Really fascinating talk, thank you. I was particularly interested in the maps that showed the tracking of where the vehicle has gone. Some places it appeared to go very purposely and broadly one direction. I wonder what was happening where it appeared to be scrabbling around and going over the same things. Had it found something it was looking for, or was it not yet finding what it was looking for, or did it find something that it hadn't been looking for and was surprising it?
A little bit of everything. Thank you for that question. So rover driving works by you make a long-term plan. You look at the orbital images, what's hanging in the courtyard now, more detailed orbital images. You map them. Some of you might have spoken to Matt Ball, Peter Forden, and many others who stood around that table with the maps. So you have a good idea, like a map on Earth, what you might find there. And then you go there and you look at it. And you look at it with a rover, but you make that long-term plan. And we have a person who is called the long-term planner. And the long-term planner draws a list and says, in this area, in this next 2 kilometers, we need to do this, this, and this. Because we have developed a hypothesis and a couple of questions, what we wanted to investigate there. And then there are people like me who do the tactical planning. And I'm the Science Operations Working Group chair. So on any given day, the rover has driven. We get the pictures at 4 a.m. At 8 a.m. we start planning. Okay, where are we? What of that list can we do today? And what you see here are either, in yesterday's images we have this. Let's go back. But most of the time when we have seen from orbit that this is a very interesting area, and we have a long list of things to tick. So we drive up there and we say we can tick this box here. We still have that question, but the rock that likely answers this is over here, so drive here. Now we might need to come back because we can't go straight because the terrain doesn't allow it. So we come back. And then we want to go here, and we have to come back out again because that terrain isn't drivable. We need to get back out here, but we needed to get into that area. And then we go around and we look just like an explorer would. And we need to be driven by what we see. But then there are also areas from like Yellowknife Bay all the way past Kimberley, where we said we know what these plains look like. They look like the same from orbit. We just make a few stops to confirm that we are right. But other than that, we drive, because we are always very conscious of rover lifetime. You can't go and repair it. You have to make the best use. And so we are trying to strike that balance between in-depth investigation, which we called campaign, and we are currently in the boxwork campaign, so we are going back and forth and doing all of this, and driving for distance. We now know how the boxworks looks. Let's get out of here and get to the next stop. And that's how it works. So I think we had a question here. Yeah.
Yes, a quick one. What happened to the wheels, and how long do you think they will last?
The wheels are actually a very clever piece of engineering. What happened is sharp rocks here and there, wear and tear. But they have grousers and a metal sheet. And as long as these grousers are intact, it's fine. The holes look impressive. We are picking up more sediment, which gets into the gears and that kind of thing. But as long as the grousers are, like these little bigger, thicker areas are intact, all is fine in the world. However, we can shed parts of it, if especially the outer parts get damaged because we hit a rock, unfortunate, or rock moves that wasn't foreseeable, then we could shed parts of it. So it's a very clever piece of engineering, and I personally think they are fine. They look grim, but they are fine.
How long will they last?
You know, this is a question for how long will my knee last, right? And rover lifetime, I mean, it is a valid question, but it is also an unanswerable question. In contrast to my knee, when my knee gives in, I can go to the doctor and they can put a plastic or metal knee in there. There's no one to repair Curiosity. So it is that balance that you need to strike between, building it and over-engineering it, but then also having something that lasts. And the wheels, we have 2 computers on board, we have 2 navigation cameras, so everything that we really need is so over-engineered, it will outlive anything else. Most rovers actually die by electronic fault. That's how all our predecessors have died, and that's a sudden death you suddenly don't hear from your spacecraft.
No, I won't cry on stage, I promise. I think the mic has already gone to a young man at the back there.
I've got 2 questions.
Go for
The
it.
first one is, how long was there water on Mars? And the second one is, how much liters of water are there on Mars now?
2 excellent questions. So water arrived on Mars when the planet had cooled. So Mars is 4.5 billion years old, and it needed about 100 million to cool down to a temperature that water wouldn't boil, right? And then it was there for about 1.6 billion years. And then most of it went to space, but some of it is still there in these polar caps. When you go back out there and you look at the stretch really high and look at the top of Mars, you see that white area? And it's about maybe 10, 15%. Some of it we might not see, we don't know, because it could be covered in dust around these polar caps. So there is some left, but not all of it, because we know some has left the planet. Does that answer your question?
Perfect.
Good.
I think there's now a microphone on the row behind, and once it's gone there, if we can pass it along 2 down once you're done, my dear. Thank you. Your question is?
If water is technically invisible, if clouds are technically invisible water vapor in the air which are condensed, does that mean there is water on Mars?
Yes. And there is still some water. It's very, very little. But the clouds that you see here are carbon dioxide clouds. Ooh. You know the CO2, the carbon dioxide, it's in the press as climate gas here on Earth. Because if you add just a little bit to our atmosphere, it has a greenhouse effect. On Mars, the atmosphere is so thin, it still has a greenhouse effect, thankfully, because that at least warms Mars to about minus 30 degrees. If it weren't there, we would be at minus 150 degrees. So it warms Mars, but just a little, because the atmosphere is so thin. And then we have about 0.13. I don't know if you're old enough to already have worked on numbers that are smaller than 1. So, very, very little percent of water in the Martian atmosphere. So there is a little bit, but only very, very, very little in a very thin atmosphere. So it's barely anything for things that you would think about. Could we live there? If you became an astronaut and went there, could you find it? Unless you could go to the polar caps, you wouldn't have a chance. You would have to make your own water through chemical processes.
We've got the mic. There's a hand that's been up waiting patiently, so thank you for that. You now have a microphone. What's your question?
If there's water on Mars, does that mean there's life?
Unfortunately, I can't answer that question because I don't know. There was water on Mars, and 3.5 billion years ago, I come a bit over here so we can actually look into each other's face, because it's a really good question. If there's water on Mars, was there life? Well, we don't know. And I like to make an analogy. If you have a smaller sibling, which is like this, and you say, can you go to the bedroom and find the cat? And they go to the bedroom and they look everywhere where they can, but they are not 6 foot tall and can look onto the wardrobe. So if the cat sits and sleeps on the wardrobe, your little sibling has no chance of spotting the cat. So they will come back and say, no, the cat isn't in the bedroom. They haven't seen it, which means they haven't seen any evidence of the cat, but the cat is still there, right? They just haven't seen it. And so we don't know if the cat is in the bedroom until we see it. We have not found any life on Mars. We have not found any evidence of life on Mars. But I quote a very famous scientist, Carl Sagan, who landed 2 landers on Mars in 1976. And what he said was, absence of evidence is not evidence of absence. Which means your little sibling saying, oh no, there's no cat, doesn't mean it isn't there. And so we don't know yet, and we keep looking, and that's the research we do here at Astrobiology OU, try to find out where to look. Like if you know the cat always sleeps on the wardrobe, you would take a chair and you would go peek, right? And we are trying to figure out where to look here at Astrobiology OU. And so, yeah, when you are a little bit older, come study biology, geology, physics, chemistry, whatever you like, come and help us. Great question.
The more the merrier. I think there's someone already with a mic, and then we'll come down to the front in a moment. In the green top.
Why would you take multiple samples of the same place in Mars? Why did you take different samples of why did you drill different holes?
We drilled different holes on a 35-kilometer traverse. So they are not all in the same place, but it's a good question because sometimes we take 2 samples in actually literally the same rock. And that's because sometimes if you only measure something once, it might look a bit weird and you are not entirely sure. And then you take a second sample and you measure again to confirm that what you measured in the first sample is actually what it is there. And that's just what we call due diligence, to make sure we are right with what we are measuring. But all of these rocks, except for very few ones, are in different types of rock. The one looks a little bit redder, the other one looks a bit grayer. You saw how different colors they all have, and you sometimes see this from the outside already, or the laser tells us they have slightly different chemistry, and that's how we make the decision where to drill. Great questions!
Brilliant
now there's
questions.
one in the front.
Hi, thanks for your presentation. We know on Earth that we find microbes in very extreme circumstances. What are the dangers that you are actually taking microbes to Mars?
That's a very good question, and you saw on the slide about Astrobiology OU the words planetary protection. So yes, there are dangers that we are taking things to Mars, but we are making really sure that that doesn't happen. We build everything in so-called clean rooms, where there are less than 10 particles of anything per cubic meter. And people have to dress up in bunny suits, and they have to go through an airlock where they get showered by air from top down so that everything goes off and everything gets sterilized. But it also gets checked regularly for biology. And if there is any, we sterilize again. So we make really, really sure that we are not taking anything. But then also, nature works a bit in our favor, because when we launch it into space. It's minus 50, it's desiccating, it's irradiated, so it gets a bit sterilized. We don't rely on it, but it would help us if we had made a mistake. And then we land on Mars after 7 months of basically sterilizing it on the way there. So we are pretty sure that we don't bring anything. However, rovers that are built like Curiosity in a Class 10 clean room are not allowed into what is special regions. Gale Crater does not have any evidence of surface water or ice. And when I'm Science Operations Working Group Chair, I have to look every single planning day for planetary protection. Do I see anything that could indicate water, and clear the day for planetary protection? And as a geologist, I can do that. But if there were, we wouldn't go anywhere near it, because our rover isn't sterilized to go to a special region. There's only one spacecraft, that's the Phoenix lander, that landed in ice. But it landed in a place that freezes over, where nothing that's known on Earth can survive. And it didn't take a radioactive power source, which provides its own heat. It took solar panels. So when it's getting cold, the sun goes down, it gets permanent winter, everything freezes over, and Mars sterilizes what we might have accidentally brought. So we take great care. Its planetary protection is what we research in, and what everyone takes very, very seriously. Thank you.
Brilliant question. We've got one down here, and then we'll come to you next. So we'll start down the bottom.
My question is that where does rover take its power? I'm assuming it's solar. If it is solar and based on electricity and then solar energy, how lucky you feel that it lasts so long in the presence of that much of currents and everything?
Yeah, so we are actually not solar powered. We have what's called an RTG, which is a nuclear power source, which means we can operate through Martian winter. The MER rover, Spirit and Opportunity, they had solar panels, and they were longer lived than we will be, because radioactive power sources decline, and at some point in 5-6 years, we will not be able to do much, and in maybe 10 years, we will not be able to do anything anymore, even if everything is still intact. And so that's just because the radioactive power declines. Solar panels sometimes get dust storms blowing them free again, and they can work for a lot longer. But they need to be angled towards the sun in winter, and so the rover can't do anything for 90 days in winter. And so there are trade-offs, and our machine is too big and needs too much power for solar panels. Where's the microphone?
On the front row of the second half.
So I've read quite a few books about space, and I remember reading something about the Curiosity rover singing Happy Birthday to itself every year. Is that actually true?
It is true. You are good. Dr. Paul Mahaffey, who was the lead scientist who built that instrument, he thought, actually, we have little actuators who shake the inlet so the sample falls in, and it can vibrate in different frequencies. We could actually play Happy Birthday, and that's what we do. You are really good. Other questions or smart comments? The stakes are going up here. Yes.
It's up here somewhere.
You've made mention of days and nights and seasons.
Yeah.
How do the days and nights and seasons work on Mars? Is it a similar diurnal motion as on Earth, or is it quite different?
Annoyingly, a day is 39 minutes longer. So if you try to be on Mars time, you get up 39 minutes every day, and that's fun for a couple days, and then you have to get up at 3 a.m. and go to work, right? And so people get really jet-lagged, and that's why missions usually do this for the first 90 days, and then they go to Earth time, which means we have to be very smart on when we plan, because we need to be aligned, and we need to be able to send our signal to the orbiter, you know? And so that's the days. And then, Hannah, I need your fist as a sun, please. So, and then we have the Earth and Mars, and the Earth goes around the sun in 365 days. Mars takes 600-something days. So when the Earth does one rotation, Mars is on the other side of the sun, And so the seasons are double the length, because then the Earth does another rotation, and then they come back together again. Thank you for the sun.
Anything I can do to help.
And so the seasons are basically double the length then here. And so we have a long winter, we have a long summer. But it works in the same way that it works on Earth. It gets really cold in winter, it gets warmer in summer. We can do more in summer, we have to heat less. And that's how it works. We are also in winter, on the coldest days of winter, we are looking for frost. We have found frost on the surface. So you can play all the games that you can play here on Earth, on Mars as well. Thank you.
Right, we've got time for just a couple more questions. Where's the mic going to get to first?
Before she wraps us all up, and I just saw someone who wanted to ask a question, and I will be at the Mars Globe for as long as my voice lasts, and I have an outdoor voice, for everyone who wants to ask a question for how long you want tonight. So, if you don't get to ask your question now, just come see me downstairs. So, where do we have more questions?
Surprise ending there, Susanna. There is one on this front row down the back.
You know me, right?
Oh, yes.
Okay, you're looking for water, and
yeah,
water is a key element in looking for possibility of life. But if you found the water, possibly, if life is eludes us, it's not there. Hopefully, that's not all a waste of time. There's wonderful things you've found out that tell you about the formation of our solar system, etc.
Yes, of course. And that's an excellent question. Thank you for it. Because, yes, of course, we go and we want to help answer this very big question about life. But when you go there, as a geologist, and I suspect you are at least a hobby geologist, we go there to find out how things work. And Mars is a wonderful analog for the early Earth. If we were standing in front of the globe right now, I would talk about a one-plate planet and a very old surface. So the Earth recycles its crust constantly. Our crust is fairly young. We can learn all about the young processes, such mountain building, the Himalayas, volcanoes in Hawaii. We can learn all of this, but the old evidence is preserved in very little places, a little bit in Australia, a little bit in the Canadian Shield. The one has lots of snakes and spiders, the other one is very cold. When we go to Mars, we have almost 2/3 of a planet that is this old crust. So we can study the geologic beginning of our Earth when we go to Mars. And that's exactly what we do. Of course, then the past diverted. Earth still has its water, Mars has lost the water, but that's why Mars is preserved. Mostly, except for the north, where the big volcanoes are, in a state that's 3.5 billion years old. We have very, very little rocks from that time here on Earth. And so, yes, we learn a lot about the early solar system on Mars and the younger solar system here on Earth. And we learn a lot if you have the chance to meet Julia Semprich. She studies Venus. That's the hot twin of Earth, about the same size and very hot in the atmosphere. Maybe a runaway climate of some sort. We are trying to figure this out, and there are spacecraft going there too. So Mars isn't the only planet we study.
Lovely. On the front just here.
So if there were lakes and rivers on Mars like billions of years ago, then how did the water survive?
So the water survived because the atmosphere was thicker, just like ours. And what happened then is that we actually lost the atmosphere. So we had a very big rock that hurtled in and made the Hellas Basin, for example. And if you have 5 minutes, I can show you that Hellas Basin on the Mars globe. It's a 2,000 kilometer wide basin. And so the rock must have been a couple 100 kilometers in diameter. It plunged in there and ejected some of the Mars atmosphere. But Mars atmosphere also gets lost more slowly. Mars is smaller than Earth, so it can't hold on to things. You know gravity. If I take that cup and drop it, I won't annoy you, Hannah.
Please don't.
Then it goes down towards the planet. She knows I will. And so that's gravity, and that holds onto everything. That's why we don't fly off the Earth. But if very, very small things, they can go all the way up, up, up and get lost to space. Earth is big, it holds onto most of things. Mars is a bit smaller, so it loses gases quicker. And so that's how all that water got lost. It was there, the atmosphere was thicker, we had all that water, and then it got taken away by two different processes. Great questions.
Question. I think there's a lovely, thank you very much.
So water on Earth, we think, came by asteroids.
Yeah.
Is it the same for Mars, that we believe that the water that was on Mars potentially also came from asteroids?
And that's because all of our terrestrial planets were molten balls of rock that would have had an atmosphere, but over a molten rock, like, you know, the basalts of Hawaii, when you see these images, that's about 900 degrees. And so the surfaces were all very hot, and then they cooled down, and then they could have liquid water from two sources. The one is the comets, and that's just how our solar system formed. I need a sun again, please. So we have the sun, and we had this dust disk. But it was very hot here, and it got colder and colder and colder. And so the small things, such as water, they would have condensed out here because they are condensing far away from that source of heat. And things that are condensing easier, like iron oxides and so on, they could condense here. So you had that chemical gradient, and you would have all the comets and so on, thank you for the sun again, that are forming in the outer parts of our solar system, and the rocky parts that are forming in the inner parts of the solar system. And then you would have these comets that bring it back in.
There's a question up in the middle, if someone can get a mic up there. If there's one closer to an edge, we'll take that while we wait. But if not, I would just keep making noises until a microphone reaches there. And microphone reaching there and me making noises is what we're at.
Thank you very
Lovely.
much.
Welcome. What's your question?
I have two questions. The first thing is Mars a possible scenario prediction? What could happen to Earth in a long time ahead? And the second question is, can you give a little bit an explanation about the practicality, how you maneuver Curiosity? So I'm wondering, how long does the signal take from Earth to Mars to give directions? Is Curiosity maneuvering on its own with some form of intelligence? So what is the speed? How many meters or it does drive per day? And you can give a little bit an insight in the daily practicalities.
Yeah, so I take the Mars is an analog for early Earth. It has now lost its atmosphere. If we are unlucky and get a very big meteorite strike that blows off some of our atmosphere, yes, it could be, but not necessarily. I think Venus would be the better analog, because if the atmosphere heats itself up, we either get a snowball Earth because of the physics that happens, or we get a very hot, and if it's getting very hot, the water goes to the atmosphere and it heats even more, and so there are options there, just from physical models. So I would think Mars is a frozen in time analog of the early Earth, more than a future prediction. Curiosity, its speed, 4 centimeters a second, all right? So we are very slow, and we are driving between 10 and 50 meters in any given planning cycle. Why is there a range? Sometimes we bump 20 centimeters, because if we are in one of these earlier mentioned and well-observed wiggly areas, we might go, okay, we are standing here, 30 centimeters from us is the next target, so we just do this, right? But if we are on these rapid transit routes, as we call them, we drive as far as we can see. It's called the view shed. And view shed is simply, I'm standing here, I can see all of you. If you are standing up there, you might not see everything downhill, and so what you can see, you can drive on. That's a very simple principle. We have some form of intelligence on Curiosity, but mind you, we landed in 2012. We launched in 2011, and Ashwin Vasavada, the principal scientist, started his job in 2004. That's when they started building. So AI wasn't quite there. Of course, computers, you can make smarter, you can upload, and we have some forms of AI. We can drive off our view shed, and Curiosity always looks after itself. So if one of the 6 bogey wheels doesn't do what the 5 others do, it goes stop, thrown home. And so it has some form of AI. Perseverance, which launched in 2020 and landed in 2021, is a much younger rover and has much more AI. And if you look, it has already in its 4 years driven further than we have in our 12. And that's partially because how the mission works and where they have the targets they want to go to, but also it is because they have more AI on board that can drive better in a terrain that a human being hasn't seen yet. And how do we do it? I look at it tactically. The long-term planner tells me, this is your list. Find what you can do today from that list. I look around and say, okay, we can do this today. But the other thing on my list, which I can't do today, is over there. And then the Science Operations Chair, not Science Operations Working Group Chair, our abbreviations and names are very difficult. He goes to the engineers directly and says, okay, the scientists are telling me they want to go there. Can we do this? And then engineers look at it. They write code because it takes 7 minutes when Mars and Earth are very close together. If we are at the opposite sides from the sun, we can't communicate at all. So on average, it takes about 10 minutes for the signal to reach Mars. If you were to do something in real time, it would go there in 10 minutes. And you would see the result in 10 other minutes because it has to come back. Now imagine, oh, I need to put the brakes on there. So 20 minutes later, you find out you have fallen down there. And that's why we do everything always autonomously. And with that level of autonomy comes that you can drive where you can see, the rover looks after itself, and you really don't want to take any risks and get stuck. And so that's how we make driving decisions, on the grounds of science, on the grounds of the viewshed, and it's always a discussion, and there's always several things to weigh. If someone asks me about the most important skill for anyone working a mission, teamwork.
Right, I've just had the signal from the back of the room that we have time for one more question, so you have lucked out. This is it. But, as Susanna said earlier, she is going to be made to stand outside the Mars. It's about a terrible thing I'm going to make her do. And so if any of you do have any more questions after this final one, you can go and join Susanna out there. So please,
okay, thank you. You talked about human bacteria and pollution of some kind going to Mars and how you try and avoid that. But Elon Musk wants to send people to Mars, and clearly they're filthy, you know, and they're going to go somewhere that you also talked about, where there's ice, because that's where the water is that they need. Yeah. So if humans go to Mars, and if they then claim to have found life, that's going to be invalid, isn't it? Because they could well be the source of such life.
That is an excellent question. That's also covered by the planetary protection. If you take a human mission, what you ideally want to have, you want to do two things. First of all, you really want to confine them to one region, and you want to really know which direction is the atmosphere blowing. So you want to really know where on Mars this contamination could go, and you want to map that. You also want to know what they bring. And of course, humans, we have a microbiome, and sterilizing is indeed not an option, because then you don't need to send them if you have sterilized them before. They would be dead, right? And so I think it's rushed a little bit. We should get the Perseverance samples back first. We should look for life first. I am all for boot prints in the rover tracks. And I'm quoting Steve Squires here, the PI of the Spirit and Opportunity rover, who has written a book that's an excellent read. Roving Mars, it's the title, Steve Squires. And he ends his book with the words that he wishes for boot prints in the rover tracks one day. But you need to get it right. You need to do the investigation before you destroy something. And so, yes, humans would destroy something, but humans would also bring a lot of opportunities. They don't need an AI to navigate. They don't need ground in the loop with usually 24 hours turnaround time to say, no, that's not interesting, this is interesting. They can be trained, they can bring all that knowledge with them. And so robotic exploration is great. Human exploration is great. You just need to apply the right thing at the right time. And I hope that in my lifetime, we have human astronauts walking on Mars with a little rover in tow whom they can tell, and you do this now while I walk over there. So that's my pipe dream. I don't know if I get to live long enough, but I mean, it's all progress, and we'll see what happens. I just hope we don't do step 2 before we do step 1.
Wonderful. Well, thank you very much, Susanna. I think I speak for everyone here when I say that was absolutely fabulous. And if you can join me in a round of applause. Wonderful.